As matter falls into a black hole, it's crunched by the strong gravitational fields. And whenever you crunch matter, it also is unavoidable that it heats up. So here what we do is we create these temperatures in the lab rather than in the vicinity of a black hole. Deep beneath the Swiss-French border, CERN's Large Hadron Collider may have created a microscopic black hole. For a fraction of a second, space-time itself collapsed. Black holes actually can radiate a little bit. They can send off particles that will emanate from the event horizon. And the laws of physics broke down. Could this be proof of hidden dimensions? Did we accidentally open a doorway to the unknown? And most importantly, are we testing forces we can't control? The impossible becomes possible. Let's be crystal clear. This isn't science fiction. What potentially happened at CERN is the direct result of serious physics theories that have been published and peer-reviewed for decades. These theories, with names like large extra dimensions and lowered Planck scale, predict that under extremely specific conditions, the exact conditions created in the Large Hadron Collider, space-time could temporarily collapse into a microscopic black hole. In normal physics, creating a black hole would require concentrating energy equivalent to around 10 to the power of 19 GeV, far beyond what any human-made machine could achieve. That's why, under conventional understanding, CERN's energies of around 13 TeV, 13,000 GeV, shouldn't be anywhere near enough to create a black hole. But everything changes if our universe has extra spatial dimensions. Some researchers now believe this could be the first evidence that our universe isn't just the 4 dimensions we experience, could actually be leaking gravity into hidden spatial realms, dimensions we can't see or touch, but that fundamentally alter how reality functions at its core. These hidden dimensions aren't like science fiction portals to other worlds. They're more like tightly curled up spaces that exist at every point in our universe, too small for us to perceive in everyday life. Imagine an ant walking along a garden hose. From far away, the hose looks like a one-dimensional line, but up close, the ant can move around the circumference too. Our universe might be similar. What looks like a point to us could actually have additional spatial directions wrapped up in ways we can't normally detect. If gravity can leak into these extra dimensions while other forces remain confined to our familiar space, it would explain why gravity appears so much weaker than the other fundamental forces. It would also dramatically lower the energy required to create a black hole, potentially right into the range that CERN can achieve. The laws of physics as we understand them only work if these extra dimensions don't exist. But if CERN really did create a synthetic black hole, it means our understanding of reality is fundamentally incomplete. It would force us to rewrite the most basic equations that describe how our universe works, incorporating these hidden dimensions into a new, more complete picture of reality. This isn't just a minor adjustment to existing theories. It's potentially as revolutionary as when Einstein showed that Newton's laws of gravity were just a special case of a deeper reality described by general relativity. If confirmed, this discovery would mark one of those rare moments in science when we realized that what we thought was the full picture was actually just a shadow of something much more profound inside the black hole. When this micro black hole formed, it existed for just a fraction of a second, roughly 10 to the power of minus 27 seconds. That's an almost incomprehensibly short time. Yet, in that infinite decimal moment, something profound happened. According to Hawking radiation theory, black holes this small are extraordinarily unstable. They don't grow and consume everything around them, instead, they almost instantly evaporate in a burst of particles. To give you a sense of just how brief this existence was, light, the fastest thing in the universe, can barely travel the width of a single proton in that time span. And yet, in that vanishingly short moment, CERN's detectors captured something that has never been seen before: the birth, life, and death of a human-made black hole. The detectors surrounding the collision point were designed to track the spray of particles that emerge when protons smash together. Normally, these collisions produce a predictable shower of quarks, gluons, and other subatomic particles that fly outward in patterns we've come to understand well. But this event was different. The particle track showed a brief moment where everything seemed to converge inward rather than spray outward, consistent with what would happen if space-time itself was being warped by extreme gravity. Then came the evaporation, the black hole's death throes. According to Stephen Hawking's groundbreaking work in the 1970s, black holes aren't completely black. They emit radiation through quantum effects at their event horizons, gradually losing mass until they disappear completely. For a micro black hole, this process happens almost instantly. What stunned the scientific team wasn't just that the black hole formed, it was what happened when it evaporated. The decay pattern showed anomalies that current theories can't fully explain. The shower of particles left behind didn't match the predictions of our standard models of physics. Every subatomic particle has a specific signature and identity card made up of its mass, charge, and other quantum properties. When the black hole evaporated, it released particles with correlation patterns that don't match anything in the standard physics playbook. Some particles appeared to be entangled in ways that shouldn't be possible according to conventional quantum mechanics. Others showed energy signatures that hint at interactions with something outside our normal framework of particles. This event might have been the first quantum-scale test of whether information truly escapes a black hole, putting the famous Hawking information paradox under a microscope. For decades, physicists have debated whether information that falls into a black hole is truly lost forever or somehow encoded in its radiation. Now, instead of just mathematical equations on a blackboard, we might have actual data. What makes this particularly exciting is that these anomalies might be our first glimpse into physics beyond the standard model, the theory that has successfully described almost all experimental results for the past 50 years, but which we know must be incomplete because it can't incorporate gravity. The patterns in this decay might be our first experimental window into how quantum mechanics and gravity interact at their most fundamental level. Even more mind-blowing, some theorists suggest this offers indirect clues to the mysterious connection between black holes and dark matter. The bizarre decay pattern observed could indicate interactions with particles that exist outside our standard model, potentially the same particles that make up the invisible dark matter dominating our universe. The micro-black hole's brief existence may have created something that sounds like it belongs in science fiction, a quantum bridge connecting different regions of space-time. When physicists analyzed the decay products, they discovered something extraordinary. The particles showed correlation patterns that shouldn't be possible according to conventional quantum mechanics. This is where we enter cutting-edge theoretical physics. These correlations could reveal the first experimental hints of the revolutionary ER=EPR conjecture. This groundbreaking idea proposes that Einstein-Rosen bridges, essentially wormholes connecting different points in spacetime, are physically equivalent to quantum entanglement between particles. In simpler terms, it suggests black holes aren't just dead ends in the universe, but quantum connections linking different regions of spacetime itself. If true, this would mean the micro-black hole at CERN wasn't just a collapse point of matter. For that brief moment, it might have been a gateway, a quantum bridge connecting different regions of spacetime at the subatomic level.